Hi, my name is Kelly Dunham, and today I'm going to be talking about electricity and magnetism in future forms of transportation. The United States is incredibly dependent on non-renewable fossil fuels for our transportation and for our electricity. In 2016, about 143.37 billion gallons of finished motor gasoline was consumed in the United States. This roughly equals about 391.73 million gallons of gasoline consumed daily, which is the highest recorded amount of gasoline consumed on record. Gasoline is a form of non-renewable energy that is refined from crude oil, which is a mixture of over 200 hydrocarbons that form from the decayed remains of organisms that lived around 50 to 500 million years ago. A gasoline-powered car works by a mixture of fuel and air traveling into an internal combustion engine, which is then ignited by a spark from a spark plug. The transmission then transfers the mechanical energy from the engine to rotate the car's wheels to make it move. Although newer cars can run on fuel that is comprised of a mixture of gasoline and ethanol, vast amounts of non-renewable gasoline reserves are used each year that will take millions of years to replenish. In the future, the scarcity of gasoline will create a demand for transportation that uses renewable forms of energy that focuses on electricity. Currently, the technology does exist for vehicles to run on electricity. There are some vehicles that use hybrid electrical and gasoline engines, plug-in all-electrical engines, or fuel cell technology that all use electric motors. Besides smaller consumer vehicles, some other forms of transportation can also use electricity and magnets to move passengers over large areas, such as the maglev. For cars with hybrid electrical and gasoline engines, the main source of energy used to rotate the tires to make the car move is from a rechargeable battery that powers an electric motor. However, once the battery is depleted, the car automatically switches to a gasoline-powered internal combustion engine. For cars that are all plug-in, all-electrical engines, only electric motor is present. There's no internal combustion engine. For cars that use fuel cell technology, they rely on a tank that uses some form of hydrogen from either methane or hydrogen gas. The gas then feeds into a fuel cell stack, which uses hydrogen and oxygen atoms to catalyze a chemical reaction that takes place at two electrodes. The electrodes pass free electrons through the fuel cell to the electric motor and usually only create water as a byproduct. There's some issues with fuel cell stack technology, though, because of potential issues the reactivity of hydrogen gas. Hydrogen gas is an oxidizer that is extremely reactive. It can ignite using 1/10 of the energy required to ignite gasoline, which could be very dangerous in a potential car accident. For each of these types of cars that use an electric motor, the motor uses two different types of magnets to create rotational motion. The basic design of an electric motor consists of a rotating electromagnet connected to a battery that is between a permanent field magnet. The electromagnet is known as the armature, which is comprised of a metal core surrounded by a thin wire that is wrapped around the core. The permanent field magnet surrounds the armature in a U shape that has a designated north and south pole. When the car is turned on, an electrical current will travel from the battery to the wire surrounding the armature and finally to the metal core of the armature. The armature will become a solid metal of free-flowing electrons that travel throughout the entire magnet. The electrons will produce a delocalized negative charge that causes the armature to rotate because the polarized north and south poles of the magnets will be either attracted or repulsed by the negative charge. If the armature is centered between the two magnets with a strong enough electromagnetic field created by the electrical current, the armature will constantly be repulsed and attracted by the opposite sides of the field magnet. The armature is attached to an axle which turns and creates rotational motion, which is with the electrical current and electromagnetic field are applied to it. Although this technology is more common in smaller vehicles that people can own privately and drive, this same electrical motor and fuel cell stacking technology could be applied to larger vehicles like vans and buses that act as public transportation. The other form of transportation that I'm going to talk about is maglev trains. For some forms of long international transportation like jet planes, there are probably not many future electrical options to decrease the plane's dependence on jet fuel, but other high-speed forms of transportation are available, like the maglev train, which is short for magnetic levitation, and it was first developed by James Powell and Gordon Danby in the Brookhaven National Laboratory in the 1960s. Maglev trains use superconducting magnets that reach extremely low temperatures that are around negative 267 degrees Celsius. As the temperature decreases to extremely low temperatures that get closer to 0 Kelvin, the circuit's electrical resistance becomes non-existent. From Ohm's law, it is known that the voltage of a circuit is equal to its current and its electrical resistance. When the electrical resistance becomes non-existent, the electrical potential or voltage will be directly impacted by only the electrical current in the circuit. The superconducting magnets create incredibly strong electrical fields with large amounts of electrical current, which creates strong magnetic fields. The track a maglev train uses is comprised of magnets with a north and south pole. The superconducting magnet is placed underneath each individual train car with its own north and south poles. The like poles of both magnets cause the train to be repelled from the track and is pushed upward, causing levitation, while the opposite charges in the magnets cause an attractive force that makes the train move forward. Since maglev trains rely solely on superconducting magnets, they do not use any form of fossil fuels. Also, the maglev trains do not use train conductors or drivers since the maglev is only guided by the magnets in the track. Maglev trains can travel as fast as 375 miles per hour and may be able to travel from New York City to Los Angeles in 7 hours. The first commercially available high-speed maglev train was opened in Shanghai in 2004. Currently, the possibility of maglev trains has been explored in the United States for short routes from Baltimore to Washington, D.C. Altogether, the electrical and magnetic technology required to use transportation that does not rely on fossil fuels does currently exist, but a demand by American consumers and government investments into this technology must be utilized to make these types of transportation available everywhere. The amount of gasoline and coal in the world is limited, so we have to look more into several renewable energy sources to power these forms of transportation, like hydroelectricity, solar, wind, and geothermal, that can produce the electricity we need to rely on fossil fuels less. And can power the electricity that we need for our cars and the superconducting magnets in these maglev trains. That